Could the speaker of the next talk, the presenter of the next talk, please speak up? Is it Arissa?
Yes, that's me.
Oh, great. Let me make you the presenter. So please go ahead, and in a minute, you can go ahead and start sharing your slides and take it away. So the next talk is on training EfficientNets at supercomputer scale. That's interesting. 83% ImageNet top accuracy in 1 hour by Arissa Wongpanich from UC Berkeley. Sorry if I mispronounced your name. Take it away.
Great, thank you so much. Hello, everybody. I'm Arissa, and I'll be presenting some of my work on training EfficientNets at supercomputer scale. So this work was done in collaboration with folks at Google Research, UC Berkeley, and the National University of Singapore. In this work, we explore optimizations required to scale training of EfficientNets to large batch sizes on a large cluster of TPU cores. We also present timing and performance benchmarks for EfficientNet models trained on the ImageNet dataset in order to analyze the behavior of EfficientNets at scale. So I'll start off with some background. As we all know, deep learning is extremely computationally intensive. As machine learning models have gotten larger, as we can see with large models like Google's BERT or OpenAI's GPT-3, so has the need for increased computational power. Large clusters of specialized hardware accelerators, such as GPUs and TPUs, can currently provide computations on the order of petaflops. And this has allowed researchers to dramatically accelerate training time. For example, last year, some MLPerf results from Google showed that the ResNet 50 image classification model can be trained on ImageNet in 30 seconds on 4,096 TPU cores. And this is to a target top 1 accuracy of 75%. So with so much compute, the question arises, how can we fully utilize this compute? One answer is with data parallelism. So with data parallelism, the mini-batch is distributed across multiple nodes. And each node, or in this case, TPU core, computes its local gradient on its own portion of the data. Then each of the node's local gradients are accumulated to get the global gradient, which is then propagated to all of the nodes. So some of the challenges that we observe with this approach include the degradation of model accuracy when training with large global batch sizes, namely batch sizes of 16,000 or greater. Additionally, the default TensorFlow APIs for TPU, called TPU Estimator, constrains evaluation to be performed on a separate TPU chip, and this creates a new compute bottleneck from the evaluation loop. So here I'll go into more detail about some challenges we face at scale. Training machine learning models with more TPU cores requires increasing the global batch size, and this is to avoid underutilizing the cores. This is because TPU cores operate over a memory layout of XLA, or the Accelerated Linear Algebra compiler. And so the XLA compiler pads each tensor's batch dimension to a multiple of 8. This means that when the number of TPU cores increases to the point that each core processes fewer than 8 examples, the cores will have to process padded examples, thus wasting resources. Thus, we can see that training on an entire TPU pod, which has 2,048 TPU cores, requires at least a global batch size of 16,000. And it's been observed previously in the literature that when we train at such large batch sizes, there's a degradation in model quality compared to models trained with smaller batch sizes. And this is due to a generalization gap described in a paper by Keskar et al. Additionally, we also face compute bottlenecks when training across large numbers of TPU chips. So next I'll talk about some of our contributions in this paper. So our work is based on scaling up EfficientNets, which is a family of efficiently scaled convolutional neural nets, which have recently emerged as state-of-the-art models for image classification tasks. Recently, the EfficientNet B7 has been able to achieve 84.4% top 1 accuracy and 97.1 top 5 accuracy on ImageNet. And I believe even more recent results, which iterate or provide variations on EfficientNet, have been able to improve upon this as well. So EfficientNets operate by optimizing for accuracy as well as efficiency by reducing model size and floating point operations executed while still maintaining model quality. The networks are scaled across 3 dimensions: width, depth, and resolution, using a compound scaling factor, as we can see in the figure. Currently on Cloud TPU V28, which provides 8 TPU cores, it currently takes 23 hours to train EfficientNet B0 model. By scaling up EfficientNet training to just a half TPU V3 pod, however, we can significantly reduce this training time, providing a 23% or 23 times speed up. So now I'll discuss some of the optimization techniques that we used to scale EfficientNet training on a TPU pod. While the original EfficientNet paper used the RMS prop optimizer, it's known that with larger batch sizes, RMS prop actually is not able to maintain model accuracy. So instead, we decided to use the layer-wise adaptive rate scaling optimizer proposed by Yu et al. And using the LARS optimizer, we're able to scale up to a batch size of 64K while attaining similar accuracies as the EfficientNet baseline accuracy in the original paper. In addition, in order to maintain model quality at large batch sizes, we also modify learning rate schedules. So we adopt learning rate warm-up and linear scaling techniques, which are found in previous works to scale to large batch sizes. So for linear scaling, it's been found that increasing the global batch size while keeping the number of epochs fixed results in fewer iterations to update weights. So in order to address this, we apply a linear scaling rule to the learning rate for every 256 samples in the batch. However, with such large learning rates, we found that larger learning rates can lead to divergence. So we also have to apply a learning rate warm-up where training starts with a smaller initial learning rate and then gradually increases over a tunable number of epochs. In addition, we compared various learning rate schedules such as exponential decay and polynomial decay and found that for the LARS optimizer, a polynomial decay schedule achieves the highest accuracy. So we also contribute a distributed evaluation optimization technique. So we find that the execution of the evaluation loop is actually another compute bottleneck on the standard cloud TPU implementation of EfficientNet, since evaluation and training loops are executed on separate TPUs. With the traditional TPU estimator, evaluation is carried out on a separate TPU, and training executes faster than evaluation, causing the end-to-end time to depend heavily on evaluation time. With distributed evaluation, however, both train and evaluation are distributed on all the TPU accelerator cores, and this allows for scaling to larger numbers of cores. Additionally, we distribute the batch normalization across cores by grouping subsets of cores together. So in a distributed training setting, a common practice is to perform batch normalization per replica, and this reduces the cross-device communication cost. However, in practice, we found that the batch normalization batch size or in other words, the per core batch size, has a critical effect on the final validation accuracy achieved in the model. So we carry out batch normalization with a distributed reduction across a small number of peers to compute the mean and variance on a subset of replicas. This gives us more control over the batch normalization effective batch size and effectively decouples it from the global batch size as well as the number of cores. Finally, we also use mixed precision training with bfloat16. So in this work by Jia et al., linked below, it's been observed that using the bfloat16 floating point format for training convolutional neural networks can actually match or even exceed the performance of networks trained using traditional single precision formats such as floating point 32. So this is possibly due to a regularization effect of using bfloat16. So since the majority of the computational and memory access overheads in EfficientNet are in the convolutional operations, we use bfloat16 for convolutional operations with minimal loss in accuracy. And for all non-convolutional operations, such as batch normalization, loss computation, and gradient summation, we use 32-bit floating point numbers to maintain comparable accuracy with other 32-bit floating point networks. So now we provide some results from combining the techniques described previously to train a variety of EfficientNet models in the ImageNet dataset on different TPU pod slice sizes. So we trained for 350 epochs to provide a fair comparison between the original EfficientNet baseline and our methods. As we can see in this graph, the x-axis shows us the number of TPU cores that we've scaled up to, and the y-axis shows the time to peak accuracy. So we benchmark training times and accuracy by taking an average of 3 runs for each set of hyperparameters and configurations, and the training time is measured by computing the time immediately after initialization of the distributed training and evaluation loop to the time when the peak top 1 evaluation accuracy is achieved. So we're able to observe a training time of 18 minutes to 79.7% accuracy for the EfficientNet B2 model on 1,024 TPU cores with a global batch size of 32,000, and this represents a significant speedup. Also, by scaling the global batch size up to 65,000 on 1,000 TPU cores, we're able to reach an accuracy of 83% in 1 hour and 4 minutes for the EfficientNet B5 model. So next we can see a table that shows the full benchmark of accuracies and respective batch sizes. So in order to maintain accuracy at such a large scale, we needed to tune multiple parameters. This includes optimizer, base learning rate schedule, and the learning rate warmup. So we can see that using the Lars optimizer instead of the Armis prop optimizer allows us to scale to large global batch sizes. Empirically, we also found that using a polynomial learning rate schedule works better with Lars. So as we can see in the bottom row, with our methods, we're able to maintain an accuracy of 83% on EfficientNet V5 model, even as the global batch size increases to 65,000. Additionally, we provide a comparison of communication costs and throughput as the global batch size and number of TPU cores scales up in this table. So we can see that as we increase the number of cores, and thus the global batch size, the throughput, or number of images that are processed per millisecond, scales up linearly. In other words, the step time remains approximately the same at scale, which means that it's promising if we wish to scale up even further to a full TPU pod or even multiple TPU pods. So for a preview at some future work, we hope to conduct a deeper study on some other large batch optimizers for EfficientNet. one optimizer that we want to look at is the shampoo optimizer, which is a preconditioned gradient method, as well as the SM3 optimizer, which is a memory efficient optimizer. And both of these optimizers have shown good performance for large batch size training on other models, so we think that it could be a promising area of future research for EfficientNet. In addition, model parallelism is another future area of exploration, which would supplement the current data parallelism to allow training on large numbers of chips without having to increase the global batch size. So thank you so much for listening. And if there are any questions, I'll be happy to take them.
Wonderful. Thank you, Arissa. That was an excellent talk. So let's open up the floor to questions. Feel free to unmute yourself and ask questions.
So, Arissa, I have one question. Sorry, Jairam, can I ask one question?
Yeah, go ahead. Sorry.
Okay, no. Okay, thanks. So, Arissa, you said that with very large batch sizes, the model may not converge to like the loss may be high, right? The converge loss may be high. So, in that Facebook paper by Goel that we did ImageNet in 1 hour, they scaled linearly the learning rate also with the batch size, right? And they were able to work up to, I think, 8K, right? Or something, right? Batch size. So did you try that linear scaling of the learning? And I think in your slide, I saw linear scaling and warm up, right? But then what happened?
Yes. Yes, that was actually one of the methods that we used. So we did follow the approach taken in that Facebook paper, and it did prove to be helpful in scaling to large batch sizes of 64,000.
Oh, so that helped, right? Okay.
Yes.
Okay. So, okay. But they did not work with Lars optimizer. I think they were using RMS prop, right? Probably, right? Or something. Yeah.
Yes.
Okay.
I think that paper was not using Lars optimizer at the time.
Yeah. And one more question is that you use batch normalization, right? And so recently there is a paper which says that normalization pre-training just recently came in which they did not use batch normalization and they used gradient clipping, right? And with EfficientNet, they were able to achieve up to 85.6% accuracy of ImageNet. So I think because we were also struggling with batch normalization. Batch normalization performance is not very predictable, right? Sometimes you may improve, sometimes it may not, right? So yeah, so I think just to tell you that I came across this work, so you may be interested in that. It just a paper is called high performance large scale image recognition without normalization. Okay, so
Great.
yeah.
Thank you.
That's very thank you. Very interesting talk. Very relevant. I liked it. Thank you.
Great.
So,
Thank you so much.
Yeah, I have a question, Arissa. So, how generalizable is the approach of using the LARS optimizer? So you've shown excellent results with EfficientNet. Have you tried it with other models? Do you think that this optimizer will help other models scale to a large number of TPU cores as well?
Yeah, so I think that the Lars optimizer has there have been some works on other models such as ResNet. I believe that Google's machine learning performance benchmark actually uses the Lars optimizer as well for their ResNet 50 results. So I think for image classification models, I think Lars is pretty generalizable. For other models like language models, I think there's an optimizer called LAMB, which is based on Lars and has also shown good results for models like BERT.
Great. Okay. Thank you. Questions?
Yeah, one other question I have. Thank you so much, Arissa, for this excellent talk. Have you considered using some compression techniques for this neural network? And do they think they have like any potential to improve the scaling or the efficiency of this training even further?
Yeah, that's a great area that we could look into some more. I have not done too many experiments on that for EfficientNet yet, but yeah, that's definitely something that I could look into more.
Thanks.
Great. I think we're out of time. So thank you very much, Arissa. And